Okay, good morning, everybody. So what we're going to be doing today, we're going to be doing inverse Laplace transform. However, before we do that, I found something and I thought we'll share it with you. So I'm going to run it in MATLAB. We have MATLAB now on our machine, so we can run more simulation here in the class.
She sells seashells. She sells seashells. She sells seashells.
Okay, so I'm going to play 3 audio for you. And you're going to try to tell me, you're not going to be able to tell me, but try to distinguish between the clarity of the audio, and then we'll talk about it.
She sells seashells. She sells seashells. She sells seashells.
Which audio is clear? And
3.
and 3 and 3 and 2 is not very clear, isn't it?
Yeah.
So what's happening here? I mean, let's just look at. So this is the spectrum of the sentence that was read. She sells seashells. Now, if you look at the letters, okay, so what this shows, this is the time axis, and this is the frequency content. And the way it's plotted by taking the spectrum and overlapping the time. Does that make sense? So at this, when it says she, this is the spectrum for it, but then we overlap the E with the ish, so we have a continuous spectrum that looks like this. Does that make sense? Yeah. Okay, so if you look at some letters, we notice that these letters and this graph, the color, shows you the contents of the sound. So here, for instance, most of the spectrum are happening in the middle. Here, it is a low frequency. This is the frequency. This is at high frequency, low frequency, high frequency, in the middle, low frequency, high frequency. Make sense? So this is the sentence when it is read at normal sampling rate. Now in the second sample, what happens, we downsampled. So we have a sample, 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 sample. We took this sample, we ignored this sample, we took this sample, we ignored this sample. What's going to happen when we do that? We're going to have aliasing. Does that make sense? Yeah. Because we reduce the sampling frequency by half. So if you look at the spectrum of the signal, originally, it looks something like this. There is no aliasing. And this is omega s. If I reduce omega s, what am I going to have? I'm going to have a signal that looks like this. If I reduce it by half, and now we're going to have aliasing. This spectrum is going to shift, and we're going to start having aliasing. And this is what we see in the second case. When we have high frequencies, when we have a high frequency, it's going to get aliased and come back to low frequency. Make sense? All the high frequencies here are going to get aliased and come back to the lower frequencies. Now in the third case, what we've done, we reduced the sampling by the same thing. However, we pass the signal first to anti-aliasing filter. So we pass the signal to an anti-aliasing filter that will remove any content that is above that frequency. And therefore, when we reduce the sampling, there is no aliasing. Does that make sense? And you can see the clarity of the sound when we run it.
She sells seashells. She sells seashells. She sells seashells.
Make sense, everybody? Okay. If anybody interested, you can take the code and investigate it further if you're interested. Okay. So what we're going to be doing today is we're going to look at inverse Z transform. And as a reminder, the first midterm will be posted after the class. And which will be due noon tomorrow.
So less than 24 hours.
We really need those extra 15 minutes?
It will be due at 1:15 tomorrow.
All right, yes.
So now you have no excuse. If you kept it at noon, at least you'll have an excuse.
No good excuse, yeah.
Okay. So in the previous class, we looked at the properties of the Z transform. And I just want to go back to the last example, what we've done. Oh, we've done it. Okay, looks like we finished the previous example. Okay, so we're going to do one more example on the properties, and then we're going to move to the next topic, which is the inverse Laplace transform. Only if I can find lecture 10. There we go. Okay. So this example, we're going to compute the convolution of x1 of n, which is equal to 1, -2, 1, and x2 of n equal to 1, 0, and n between 0 and 5. So we have two signals that we want to calculate the convolution for. The first is a 1, -2, a 1, this is a 2, this is x1, and x2 is just a constant 0, 1, 2, 3, 4, and 5. And what we want to do it using the properties of the Z transform. So if you look at the properties of the Z transform, we know that if we do convolution in the time domain, what is it going to be in the frequency in the Z domain? Multiplications. So therefore, I'm going to take x1 of Z. What is x1 of Z going to equal to? One
Plus
Z to the 0 plus -2 Z to the -1 plus 1 Z to the -2. X of n, Z to -n, this is 0. X of 1, Z to -1. X of 2, Z to -2. And similarly, I'm going to take x2 of Z, which is going to equal to 1 Z to the 0 plus 1 Z to -1 plus 1 Z to -2 plus 1 Z to -3 plus 1 Z to -4 plus 1 Z to -5. Now x1 of n convolved with x2 of n is going to have a Z transform that is x1 of Z multiplied by x2 of Z. And therefore, if I multiply these together and put the terms that are similar together and cancel terms that cancels out, I'm going to get a 1 minus Z to -1 minus z to negative 6 plus z to negative 7. And therefore, so please do this as a homework, multiplying these two polynomials to get this expression. Okay, so having x of z, I can find the inverse z transform. What is the inverse z transform of this? One, negative 1, 0, 0, 0, 0, negative 1, and 1. So therefore, x1 of n convolved with x2 of n is going to equal, and this is our 0 reference. It's going to be 1, negative 1, 0, 0, 0, negative 1, and 1. And of course, we can verify that. I'll let you do it at home. How do we verify this? We can do graphing, we can do the table. 1, negative 2, 1, 1, negative 2, 1, 1, negative 2, 1, 1, negative 2, 1, negative 2, 1, 1, negative 2, 1, 1, negative 2, 1. And then we're going to add them diagonally. So this is going to be 1, negative 2 and 1 is going to be negative 1. Then they're going to start canceling, 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 canceling. And then we're going to have negative 1 and we're going to have a 1. Is that clear, everybody? Okay. Any questions? Okay. So the next thing we're going to look at is the calculation of the inverse z transform. And after we calculate the inverse z transform, we're going to use the z transform to relate the difference equations and the frequency response and the discrete time Fourier transform. So it's going to give us lots of tools that we can use to better understand the system. So inverse z transform. So we know x of z is equal the summation from n equal negative infinity to infinity, x of n, z to negative n. And the question is, how do we calculate x of n if we are given x of z? And as you recall, or those who might recall, there are three ways to do this. The first method is analytical. And to do that, we have to calculate x of n equal 1 over 2 pi j integration over a closed contour of x of z, z to n minus 1 dz. So this is integration over a closed contour in counterclockwise direction. So this is how you can calculate it analytical. However, we're not going to be using this method. The second method is using power series expansion. And this uses long division. And we'll do example on this. And the third method that we will be using is using partial fraction expansion. And then if you do partial fraction expansion, we can use tables and we can use properties of the Z transform in order to calculate the inverse Z transform. Together? So again, we're going to look at the power series expansion, and then we're going to look at the partial fraction expansion. So let's look at the first method, which is the power series expansion. Or the long division method. And here I'm going to assume that we have a right-sided sequence. Which means a sequence that starts and goes to the right. So what is the idea behind this method? By definition, x of z is a power series in z to the negative 1. And therefore, we can read the coefficients directly from this polynomial, where the coefficients of z to the negative n is x of n. What does this mean? So what this means is if we are given x of z, that is a numerator over denominator, we can perform long division and then we can read out x of n. So let's do an example. So let's say we have x of z that is equal to 4z squared minus 5z minus 1 divided by z squared minus 1 over 4z minus 3 over 8. So I have a sequence x of n that has x of z that is given by this. I want to know what this x of n is. So what we're going to do, we're going to use the long division to find what x of n is. So what we do, we come here, we're going to take the numerator, divide by the denominator. We have 4z squared minus 5z minus 1 divided by z squared minus 1 over 4z minus 3 over 8. So when you use the long division, if the sequence is right-sided, we're going to have the coefficient with the highest order at the beginning. So we're going to have this in descending order. Make sense? So especially on an exam or a homework, if these are flipped, you have to have them such that this is the highest order in the polynomial, this is the highest in the polynomial, and in descending order.
In their equivalent, right? Like, the order doesn't matter.
The order does not matter, but in the
Except
calculation it will matter.
Yeah, okay.
Does that make sense? If it is right-sided, you have to have the highest order. If it was left-sided, you have to have the lowest order. Okay, so if we divide these two polynomials, what is 4z squared over z squared? A 4. Then we multiply, we're going to get 4z squared minus z minus 3 over 2. What do we do next?
Subtract.
We flip the sign. We subtract them. This is going to become positive. This is going to become positive. We add the two together. We're going to get a negative 4z plus 1/2. What do we do next? We divide. What is 4z plus 1/2 over z squared? Oh, this is negative 4. Negative 4 plus 1/2. What is negative 4z divided by z squared?
4z to the negative 1.
Excellent. Minus 4z to the negative 1. We multiply. We're going to get negative 4z plus 1 plus 3 over 2 multiplied by z to negative 1. Together? Is that clear? Negative 4z to the negative 1 by z squared is going to be negative 4z. Negative 4z to the negative 1 by 1/4, 4 with 4 cancel, and plus z would cancel, and then plus 3 over 2 multiplied by z to the negative 1. We do the same thing. We flip the signs and we add them together. So it's going to become positive, negative, negative. And we're going to get negative 1/2 minus the 3 over 2, z to negative 1. And we're going to do the same thing. We're going to divide. What are we going to get? Negative 1/2 z to the negative 2. Is that clear? So we do the same thing. We multiply. We're going to get minus 1/2. And then we're going to get plus 1 over 8 z to negative 1. We're going to get 3 over 16 z to negative 2. We flip the sign. It's going to become positive, negative, negative. We're going to get negative 13 over 8 z to negative 1 minus the 3 over 16 z to negative 2. And we continue. So what is it we've done? What we're saying is that given this expression, this is x of z. X of z was equal to 4z squared minus 5z minus 1 divided by z squared minus 1 over 4z minus 3 over 8. This is equal to 4 minus 4z to negative 1 minus 1/2 z to negative 2 plus negative 13 over 8 z to negative 1 minus 3 over 16 z to negative 2 divided by z squared minus 1 over 4z minus 3 over 8. Agree? This is what this division is, the quotient remainder. Okay. So if this is what x of n is x of z equal to, how do I get x of n from this expression?
Inverse Laplace.
I can just read it from these terms, isn't it? What is x of n equal to? I have 4z to 0. So what is x of n equal to when n is equal to 0? A 4. And then I have a negative 4 z to negative 1. So when n is equal to 1, what is x of n going to equal to? Negative 4. And then I have negative 1/2, and then so on and so forth. Does that make sense?
So, when do you stop for the remainder? Like, is it just infinitesimal?
Well,
that remainder is too small?
Well, you can, I mean, two things could happen. You could divide and then end up with no remainders, and then you're done. The other thing that could happen, this could go on forever, but you might be only interested in the x of n when n between a certain value and certain value. Does that make sense? So this is the drawback of this method is does not give you a closed loop solution, and therefore you're going to have to go forever in order to get all the x of n. So therefore we can write here, this does not, no closed form solution. And it might go on forever. Make sense? However, if I'm only interested, for instance, in x of n when n is equal 0 and 1, the first two terms or three terms, it might be a quick method just to calculate it. Okay. The second method, or the third method, but the second that we're going to be covering, is using partial fraction expansion. What do we do with partial fraction expansion? We take a rational expression and try to break it into simpler terms. And these simpler terms, we're hoping we can just, by using the tables, find the inverse for. Okay. So if we're going to use the partial fraction expansion, first thing we're going to do, if it's not already, we're going to express x of z in positive powers of z. What does that mean?
No, z is negative.
Yeah, so we know, for instance, 1/2 u of n has a z transform that is z over z minus 1/2, isn't it? But you might find this written as 1 over 1 minus 1/2 z to negative 1. Both of them are valid, and depending on the book or the reference you use, the convention might be like this or like this. So for our purpose, we're going to express numerator and denominator in positive powers of z. So if I have an expression like this, I'm going to multiply numerator and denominator by z to get rid of the negative powers of z. Second, if the numerator order is greater than the denominator order, what do we call this? Call it non-proper. And therefore, we're going to use long division until we get the order of the numerator less than or equal that of the denominator. So for instance, if I want to find x of z equal to z cubed plus 3 multiplied by z divided by z squared plus 5z plus 1, I notice that the numerator has a higher order than denominator. Therefore, I'm going to divide it z cubed plus 3 multiplied by z divided by z squared plus 5z plus 1. This is going to be z. z cubed plus 5z squared plus z. We subtract, we're going to get negative 5z squared plus 2z together. So we can write this as equal to z plus negative 5z squared plus 2z divided by z squared plus 5z plus 1. And then I can use partial fraction expansion on this term, and I can readily find the inverse of the first term. Is that clear, everybody? Okay. Partial fraction expansion on this term. Okay, the third step.
Wouldn't it be minus 2z, not 5z
Minus 2z.
in the numerator? Is like 3 minus 5 is 2.
No, this is z.
Oh, yeah, z squared.
This is z squared. Okay. The next step, we're going to divide x of z by z, and we're going to expand x of z divided by z into partial fractions. Together? Now this is a tricky step. What we're going to do, we're going to take x of z, we're going to divide it by z, we're going to expand, then we're going to multiply back by z. We'll see why. Okay. So when we do partial fraction expansion, we can have simple roots, and therefore we're going to expand them as ki over z minus pi, or we can have multiple roots or repeated roots, and in this case we're going to expand them as ki1 over z minus pi plus ki2 divided by z minus pi all the way to kin divided by z minus pi to the power of n. Remember that? If this root is repeated n times, then we're going to have n terms here that will expand as. So if I have in the expression, for instance, z minus 5 squared, I'm going to have two terms. Oh, this should be squared. And then cube, and then so on and so forth. Together? Okay. If we have complex conjugate roots, we can treat them as simple poles. So in this case, the coefficients will be complex. Or we can keep them as quadratic and expand them. So we can expand them as ki multiplied by z minus a cosine omega divided by z squared minus 2a cosine omega multiplied by z plus a squared plus k2 multiplied by a sine omega divided by z squared minus 2a cosine omega multiplied by z plus a squared. And in this case, we have poles at a e2 plus 9hj omega. So if we have complex conjugate roots, we can either treat them as simple poles, the way we treated the simple poles. In this case, the coefficients will be complex. Or we can expand them as quadratic terms as we have there. Okay. So the next step, we're going to solve for the coefficients. How do we solve for the coefficients when we do partial fraction expansion? We can either have a system of linear equations we can plug in values for z, or we can use the residue theorem. And what the residue theorem says, Ki is going to equal to x of z divided by z multiplied by z minus pi evaluated when z is equal to pi. Is that familiar, everybody? Okay. We can also calculate Kin when we have repeated roots as x of z divided by z to the n multiplied by z divided by z, z minus pi to the n when z is equal to pi. Okay. The next step, after we expanded all these, so let's call this number 4 because we have it as steps. So this is 4. The next step, number 5, we multiply by z to get back x of z, and we take the inverse. And we're going to assume that we have causal sequences unless specified, and therefore u of n is implied. Okay. So let's do some examples and see how we do this partial fraction expansion and how we calculate the inverse Laplace, inverse Z transform, sorry. So the first example, which is the one we just had using the long division, we have 4z squared minus 5z minus 1 divided by z squared minus 3 over 4z minus 3 over 8. We have two poles. You can write this as z plus 1/2 multiplied by z minus 3 over 4. What do we do next?
A and B, I guess.
We're going to take x of z and we're going to divide it by z, following the steps that we laid out. So we can write this as 4z squared minus 5z minus 1 divided by z multiplied by z plus 1/2 multiplied by z minus 3/4. Together? Now we can expand this. What is this going to expand as? K0 divided by z plus K1 divided by z plus 1/2 plus K2 divided by z minus 3/4. Agree? Everybody? Okay. How do we find the value of K0? When you are alone in the desert
We would,
and your laptop is discharged.
we'd have bigger problems than this.
We're gonna multiply both sides by the denominator here, by z. And what is this f of z? We're gonna just call this f of z. And then we substitute when z is equal to 0. Together? So f of z. So this is a new function that we're gonna call f of z.
I don't think
Right.
the expansion in the denominator, I mean, the unfoiling of the denominator is right. Because, like, z½ minus 3/4 z's would be negative z1/4, not 3/4. Right?
1/2.
Z minus 3/4 z would be 3/4 z. It would be like negative 1/4 z, right?
Oh, I see what you're saying.
So unfoiling is exactly right.
Okay, so I'm gonna, to avoid a confusion, we're gonna keep it like this. I might have mistyped it. Okay. One half minus 3/4 minus a quarter. Yeah, that might. Squared minus 5z minus 1 z squared 3/4 better?
Yeah.
Okay. So to calculate K0, we're going to multiply both sides by z and substitute when z is equal to 0. What is that going to give me?
K0.
Yeah, which is going to be negative 1 divided by 1/2 multiplied by negative 3/4. Since z is equal to 0, this term is 0, this term is 0, we're going to have negative 1. And z is going to cancel, so we have 1/2 multiplied by negative 3/4. And therefore, this is going to equal to 8/3. Similarly, we can calculate K1 is going to equal z plus 1/2 multiplied by f of z. And we're going to substitute when z is equal to negative 1/2. And therefore, this is going to equal to 4 multiplied by negative 1/2 squared minus 5 multiplied by negative 1/2 minus 1 divided by negative 1/2 multiplied by negative 1/2 minus 3/4. Together? Again, the z plus 1/2 is going to cancel out from here. And therefore, we just have z multiplied by z minus 3/4. over 4. So this is going to give me a 4. We can calculate K2, which is going to equal to Z minus 3 over 4 multiplied by f of Z when Z is equal to 3 over 4. And this is going to equal to 4 multiplied by 3 over 4 squared minus 5 multiplied by 3 over 4 minus 1 divided by 3 over 4 multiplied by 3 over 4 plus 1/2, which is going to equal negative 8 over 3. Okay, is that clear, everybody? So therefore, we can write x of z. What is x of z going to equal to? 8 over 3
over z.
Okay, let's do it in 2 steps. So x of z over z is going to equal to 8 over 3 divided by z plus k1, which is 4 divided by z plus 1/2 plus k2, which is negative 8 over 3 divided by z minus 3 over 4. Then we're going to write x of z, and x of z is going to equal 8 over 3 plus 4 multiplied by z divided by z plus 1/2 minus 8 over 3 divided by z minus 3 over 4 multiplied by z. Together? So what is it we've done with this z? You see how we divided by z, then we multiplied it back again. So we did not change anything in x of z. But what is the advantage of what we've done? Is now we have terms that have z in them in the numerator. Does that make sense? So therefore, I can use the tables. Most of the tables that we will see will have z, these expressions. If I did not do that, then I'm not going to have a z, and then I'll have to look at the properties, try to massage it to fit what I'm going to see in the table. Okay, so what is x of n? What is the inverse of 8 over 3?
8 over 3 delta.
Excellent. 8 over 3 delta of n. What is the inverse of the 4z over z plus 1/2?
Or 1/2 n minus 8 over 3, 8, negative 3 over 4.
4 multiplied by negative 1/2 to the n, u of n. Okay. And then the third term is going to be minus 8 over 3 multiplied by 3 over 4 to the power of n multiplied by u of n.
What's u of n here?
U of n,
Yeah, step function.
the unit
Okay.
step function.
Okay.
And I said, we said by default, we're going to assume u of n. So, like, I could have written this like this, and nobody would have objected, because it's by default. Unless I specify it, I'm assuming n starts at 0. Does that make sense? So n is greater than or equal to 0, or I can just add u of n here. Okay. Let's do another example. We have x of z that is equal to z cubed minus z squared plus 2 multiplied by z divided by z minus 1 multiplied by z minus 2 multiplied by z minus 3. And we are given, so here, because the region of convergence was not specified, we assume the sequence is causal. However, here we're specifying the region of convergence, which is z between 2 and 3. Make sense, everybody, what I'm saying? The previous example, we did not have the region of convergence specified. We assumed it is a right-sided by default. It's right-sided unless we specify it. So here we specified it. Z is between 2 and 3. So we're going to do the same thing. What is the first step?
Multiply by x.
Divide by z. So since we have here z in the numerator, it's going to cancel out. So we're going to have z squared minus z plus 2 divided by z minus 1 multiplied by z minus 2 multiplied by z minus 3. Unlike the previous example where we have a new term that we had to expand with z, here we do not. So if we expand this, it's going to equal to k0 divided by z minus 1 plus k1 divided by z minus 2 plus k2 divided by z minus 3. And k0 is going to equal to 2 divided by negative 1 times negative 2, which is equal to positive 1. K1 is going to equal to 4 minus 2 plus 2 divided by 2 minus 1, which is a 1, times 2 minus the 3, which is negative 1. This is going to equal to negative 4. And then we're going to have k2, which is going to equal to 9 minus 3 plus 2 divided by 3 minus 1, which is a 2, times 3 minus 2, which is a 1. And this is going to equal to a 4. Okay. What do we do next? We can write x of z as equal to let's do it as two steps. X of z over z is equal to 1 over z minus 1 plus negative 4 over z minus 2 plus 4 divided by z minus 3, and x of z is going to equal to z divided by z minus 1 minus 4 divided by z minus 2 plus 4 divided by z minus 3. And we have a z.
Should there be z's in the numerators?
Yeah. Therefore, we can find x of n Now, if I look at here, in this example, the region of convergence is between 2 and 3. So this is a 2, this is a 3. Is this sequence going to be right-sided, left-sided, or two-sided? Two-sided. Because it's a annular ring, it's going to be two-sided. This is our region of convergence. Okay. So if you look at the first term, z over z minus 1, what is the inverse z transform?
1 to the n.
1 to the n, u of n. Agree? Everybody? And why did we choose it like this? Because the root here, the pole, is at 1. The region of convergence to the outside of it. And therefore, it is right-sided. What is 1 to the n u of n?
un.
just u of n. Together? 1 to the n. 1 to the n is just equal to a 1. We can keep it. 1 to the n u of n. The next term, what is the inverse z transform of 4z over z minus q? The region of convergence to the outside of it, so it is right-sided. So what's going to be? Minus 4
2 to the n,
minus 4 multiplied by
2 to the n.
2 to the n. Very good. U of n. Is that clear? What about the third term?
Plus 4, 3 to the n. U of n.
No. Because it is left-sided. Because the region of convergence of it from 3 to the inside.
3 to the
Does that make sense?
no.
So when we calculate the inverse, we have to see the region of convergence. The 3, the region of convergence to the inside of it. So this tells me this sequence is left-sided. Make sense?
No.
Okay.
I thought that the region of convergence was like not including.
It's not.
Oh,
It does not include the pole. But whether the sequence is right-sided or left-sided is determined by where the region of convergence relative to that pole.
Oh.
So we had a pole at 1. The region of convergence is to the outside of it, and therefore it is right-sided. We have a pole at 2. The region of convergence to the outside of it, so it is right-sided. We have a 3. The region of convergence is to the inside of it, so it means it's a left-sided.
okay.
It's tricky, but hopefully familiar, semi-familiar. So therefore, this is going to equal to minus 4, 3 to the n, u of negative n minus 1. Where did I get this from?
Table.
Table, yes. But we've done something similar. Where did we do that? 8. There we go. So when z is less than an alpha, where alpha is the pole,
Yeah.
then we're going to use this formula. There's a minus sign, so that's why we had a minus sign.
Oh,
Make sense?
yes.
Okay. Okay, let's do another example. However, I just want to also just emphasize again what we're doing. We're dividing by z, then we're multiplying by z. So we're not affecting. Why we're doing it? So we can get an expression here that has z in the numerator. If I had not done that, I would not have this z here. And it would have been more difficult to find the entry in a table. By dividing by z, then bringing it back, I can have it back. And I posted on our canvas a table for z transform. So you can, if you like, print it and keep it handy when you use it. Okay. Let's do another example. We're going to calculate x of n if x of z is equal to z squared divided by z minus 1 divided by z minus 1/2 squared. And it is a right-sided sequence. What is the problem with this expression?
Two same roots?
Yes, we have repeated roots. I mean, not the problem, what is the trick? Sorry. The trick is we have a repeated root. So therefore, we're going to do the same thing, x of z divided by z. This is going to equal to z divided by z minus 1 divided by z minus 1/2. squared. How does this expand as? K1 over z minus 1 plus K2 over z minus 1/2 plus K3 divided by z minus 1/2 squared. So I'm going to have two terms that are coming from z minus 1/2. Together? Of course, I could have labeled this as K0, and this is K11, K12, same thing, whatever labels you want. Okay. How do we find K1? We multiply both sides by z minus 1. We substitute z equal to a 1. And that is going to give me a 4. Together? 1/2 squared in the denominator. Okay, which one of these is easy to find? K2 or K3? K3. Because I can just multiply by z minus 1/2 squared. So K3 is going to equal to z minus 1/2 squared multiplied by x of z divided by z. And when z is equal to 1/2, and this is going to give me a negative 1. So this is going to be gone. I'm going to have 1/2 over z minus 1/2, which is 1/2 minus 1, is going to give me a negative 1. 1/2 over negative 1/2. Together? Now, how do we find K2? Yes. Yes, we can, if you like, plug in values and try to, the left term has to equal the right term. Therefore, you can plug in values. You can plug in values, unify the denominator here, and try to make it equal to a z, which is this denominator in here. Does that make sense?
Yeah.
So, any of these methods. Or, we can use the residue theorem that tells us, so this is on the side, if I have Rm over z minus p plus Rm minus 1 over z minus p squared plus R all the way to R1 over z minus p to the power of m, then R sub k is going to equal to 1 over k minus 1 vectorial, the derivative of k minus 1 divided by d by dz to the k minus 1 of z minus p to the power of m, x of z divided by z. So we're going to use this method. Nevertheless, you can use any method you like. So in our example, we're trying to calculate K2 is going to equal to 1 over 2 minus 1 vectorial and then the derivative d by dz to the power of 2 minus 1 of z minus 1/2 to the power squared multiplied by x of z divided by z, and we're going to substitute when z is equal to 1/2. Okay, so if we do that, this is going to be d by dz of z divided by z minus 1 when z is equal to 1/2, and this is going to give me a negative 4. Together? Everybody? Okay. So therefore, we can come to x of z, multiplied with z again. We're going to have 4z, 4z divided by z minus 1, plus k2, which is negative 4, divided by z minus 1/2, minus k3, which is minus 1, z divided by z minus 1/2. Squared. So therefore, and this is a right-sided sequence, so we're going to use the right-sided entries of a table. What is the z inverse of the first term? 4.
Units.
What is it?
For UN.
U of n, yes. Just remember the number z minus 1/2, z over z minus 1/2 is 1/2 to n. If this is not 1/2, 1, it's going to be 1 to n, but 1 to n is 1, so it's just u of n. The second term is 4 multiplied by 0.5 to the n u of n. And the third term is going to equal to 2 multiplied by n multiplied by 1/2 to the n multiplied by u of n.
And that's just a lookup in the table that you.
And this is just from lookup table. Together? Is that clear? Okay, let's do one more example. So find the convolution of x1 of n and x2 of n. And x1 of n is equal to 1/3 to the n when n is greater than or equal to 0, 1/2 to negative n when n is less than 0, and x2 of n is equal to 1/2 to the n multiplied by u of n. And we're going to calculate y of n equal to x1 of n convolved with x2 of n. However, we're going to calculate it using the z transform properties. We know convolution right domain is multiplication in the z domain. So I can calculate y of z, which is going to equal x1 of z multiplied by x2 of z, and then I can take the inverse z transform of y of z. Is that clear? Okay, so if I look at the first term, x1 of z, the z transform is given by negative 5 over 3 multiplied by z divided by z minus 1/3 multiplied by z minus 2. If I look at x2 of z, is going to equal to z divided by z minus 1/2. Where did I get this from? I calculated it, but we've done an example similar to this. Okay. The region of convergence for this is z between 1/3 and 2. And the region of convergence for the second term is z greater than 1/2. When did we calculate something similar to this? Or did we not calculate one like this?
It was earlier today, right?
We did a sequence that is two-sided. Okay. But this is, that sequence is two sequences. One that is left-sided, one that is right-sided. So if we add them together, they're going to give me the overall sequence. Oh, here. We have a sequence that is both-sided. It's going to give me the annular ring. So this is similar to the example we're doing. Does that make sense? So what was this, lecture 9? Page 4. Okay. So therefore, to calculate y of z is going to equal to 1x1 of z multiplied by x2 of z, which is going to equal to -5/3 multiplied by z squared divided by z minus 1/3 multiplied by z minus 2 multiplied by z minus 1/2. Together? Then we're going to take y of z divided by z, which is going to equal -5/3 z divided by z minus 1/3 multiplied by z minus 2 multiplied by z minus 1/2. We're going to expand it as, can I just write the result of the expansion since we're familiar with it now? It's going to be -2 divided by z minus 1/3 plus 10/3 z minus 1/2 minus 4/3 divided by z minus 2. And therefore, we can write y of z as equal to -2 multiplied by z, z minus 1/3 plus 10/3 z divided by z minus 1/2 plus -4/3 z divided by z minus 2. Now if I look at the region of convergence, this is between 1/3 and 2. This is greater than 1/2. What is the total region of convergence going to be? The result of the convolution is going to be the intersection of both. So it's going to be between 1/2 and 2. Together? And therefore, if I look at these terms, the first two terms are going to be right-sided or causal, and the third term is going to be left-sided. Is that clear? Makes sense, everybody? Question?
Isn't the first one left sided too because it's outside of the range?
1/3, I mean, if we plot it, we have 1/3, we have 1/2, and we have a 2. The region of convergence is between 1/2 and a 2. So for the 1/3, it's outside of it, and therefore it is right-sided. For the 1/2, it's outside of it, right-sided. For the 2, it is inside of it, it is left-sided. Make sense?
Two would also be outside of it.
No, it's to the inside of it.
So if you think of each thing, I think it's another circle of that radius.
This is, if I'm at the 2, the region of convergence to the inside of me.
Okay,
If I am at 1/2, it's to the outside of me.
got
If
it.
I am 1/3, it's to the outside of me.
Right.
Yeah, I'm sorry we took more time. I'm going to write the expression for y of n is going to be -2 multiplied by 1/3 to the n plus 10/3 multiplied by 1/2 to the n. All of this multiplied by u of n plus 4/3 multiplied by 2 to the n u of -1 minus n. Sounds good? Okay. Thank you, everybody.